Okay, so we are recording. Okay. So let's go through an example, okay? And of all the steps. And remember, the homework, it's all open book. So this is something that would be very handy to have with you as you're doing the problem, so you can see kind of the steps, because there's a lot of calculations, as we saw, that go into this. And it's easy to lose track of where you are and forget a step if you're just trying to wing it. Um, uh, as you're working on it, this is one, it's okay to plug and chug. Over the years, I've taken 3 courses on ANOVA. The first course I took on ANOVA, I plugged and chugged. I just plugged in the numbers and I chugged, and I just kind of went, I got the p-value. I know, oh, reject the null, whatever. The second course I took on ANOVA, it started to make some conceptual sense. The third course is where it's like, okay, the light bulbs went off. Now I get it. So if you're plugging and chugging, that's all right. That's okay. If some of this makes sense, as we talked about before before the break, kind of some of the conceptual ideas of why does the F work, and that's fantastic if this is making some sense conceptually. You're doing good. Okay, let's keep going. So let's work on a problem. Let me start here. Okay, I'm going to, for this example, we're going to look at possible interventions designed to increase student reading. Specifically, want to look at how much time young students spend reading for pleasure each week, not kind of required, but we're doing some interventions to try to get kids to read more for fun. Okay. And we're going to compare 2 different interventions compared to a control group that gets no intervention, kind of just the average the general population. Okay. So we're going to use the standard alpha of 0.05. So we'll only want to make a type 1 error 5% of the time. We only want to, now, given that there's 3 samples, right, reflecting 3 different populations, so it's important to keep track of which sample is which when we're doing our calculations. So for us, I'm going to, we'll have sample number 1 is our control group. That's the no intervention group, and that reflects the general population of people out there, kids out there that are kind of in business as usual sort of programs or whatever. Our second sample is going to come from the population of kids theoretically that could get a child-focused curriculum. So these kids are in a curriculum that's working that's directly targeting kids to see if to inspire them to read more. And sample 3 is going to reflect kids in a parent-focused intervention. Here you're working with parents to try to get the parents to, some skills and strategies for getting their children to read more. Okay, so those are our 3 samples. But again, remember, we're interested in the populations these samples reflect out there, and the population of kids who might get the child-focused or the parent-focused interventions. Okay, our hypotheses. Well, again, this is the beauty of, if there's a bright side for the pain of doing those analyses, the benefit is the hypotheses are always the same. In this case, our alternative hypothesis is just that the mean for each of those populations are not the same. Did I say that right? The mean for all of those populations do not have the same mean. Yes, I actually got it right there on the slide. All of the means are not the same. Do not make the mistake of saying mu1 does not equal mu2 does not equal mu3, because maybe mu1 and mu2 are equal, but they're different from mu3. So you need to kind of phrase it some way like this. The key is at least, or you could just say at least 2 of those populations have different means. We don't know which 2. Maybe all of them do, but at least 2 have different means. And the null is that they're all exactly the same. All 3 have the same mean for how many hours the child reads each week. Okay. Sample sizes, we will keep this ridiculously small because we're going to do the numbers by hand. So we have 4 kids in our control group, 5 kids in the child-focused intervention, and 5 kids in the parent-focused intervention. Obviously, 2, but anyway, we'll keep going. Very small, but we need to. I don't want to torture anyone. Hold on a second. I'm just making sure. Am I recording? Because it's not telling me I'm recording. Do you see? Is it telling you guys I'm recording?
You're recording. Yeah.
Yeah, it's kind of funny. I don't see it telling me I'm recording. Okay, good. We'll keep going. Anyway, so here's our data, and I've just kind of organized it this way. With columns for each of the three groups. We'll start with calculating the sum of squares within. All right. So to do that, we have to calculate. Think back to the slides that from earlier. We kind of go through the process. We need to calculate a few numbers to calculate those variance for the sum of squares. So to begin with, let's calculate the sum for each of the 3 groups. So I just add up 3 plus 5 plus 2 plus 2, 2, 7, 4, 5, 2, right? I'm just adding up for each of the groups, right? And then we need to calculate the mean for each group because we're going to do the variance within the group. So we need to know the group means. So 12 divided by 4 is 3, 20 divided by 5 is 4, 35 divided by 5 is 7. So those are our group means. Okay, now I know we're working on the sum of squares within, but while we're here, let's also just calculate the grand mean is 67. And the grand mean is just the sum of everybody's score. I'm sorry, the grand sum, I should say. We're doing the sum of everybody's score was 67. If we add, right, 35 plus 20 plus 12, and then divide by the total number of kids, what is that? 14 gives us a grand mean of 4.786. So we're just kind of doing that while we're here, even though we don't use the grand mean for the sum of squares within. But remember the number because we're going to need it in a few minutes. Okay, so to do our sum of squares within, we need to do the sum of squares for each of these groups. So we subtract the group mean from everybody's score. We subtract their respective group mean. So for the control group, the mean was 3, so I subtract 3 from everybody's score. For the kids in the student-based intervention, I subtract their mean of 4 from everybody's score. And for the parent group, their mean was 7. We subtract 7 from everybody's score, right? So we do those calculations. Here's the values that we get. Those are our deviations from group means, not the grand mean. It's their deviation from each group mean, right? And to get the sum of squares, we need to square those deviations so they don't, right? They're all going to, each group mean is going to cancel, each column is going to cancel out, right? Because they'll all be zeros. They'll all sum to 0. We square each of those to get the squared deviations, right? So 0411, 49014. Now these are the squared deviations from each group mean, right? And then we sum them up. So for the control group, 0 plus 4 plus 1 plus 1 is 6. The intervention students, 4 plus 9 plus 1 plus 4 is 18. The parent, it's 1 plus 1 plus 4 plus 4 gives me 10, right? So we sum up each of the groups and add that all up, and we get 34. That's the sum of squares within. So you can see what we've done is we've done a sum of squares, but instead of doing it relative to the grand mean, it's each of the, we do it separately for each, it's just their sum of square deviations from each of their group means, because we're looking at that variability within the group. So there's our sum of squares within. Great, that's nice. Let's see, you may see that kind of written mathematically, right? The sum of squares within is the sum of x minus x bar. Now you could get a little more technical where you say it's the sum of each group within the, don't worry, other notation you might see that gets more into the subscripts, that it's group, the child I in group K, if you're really into that. But I'm not going to quiz you on using the notation. Now, this is what's called an ANOVA table. And it's just a nice way of, we calculate so many numbers, and it's a nice way of organizing your results, that you know where to find stuff. Otherwise, if you're doing this by hand and it's taking you like 3 pages, you're going to have a number over here and a number over there, and on the back of this page is going to be a different number. So the ANOVA table is just a nice way to organize the numbers as we calculate them. So you can see there's a row of the sum of squares, degrees of freedom, variances for between values, and for the within, sum of squares, degrees of freedom, variance. And then we have the F and the P value, and also even the total sum of squares and degrees of freedom. So as we calculate things, we're just going to plug them into the ANOVA table, and starting with the sum of squares within is 34. So this is just our way of keeping track. It was 30, we had 34. Let's keep going. Degrees of freedom within. Now we know this one's easy, right? This is, you know, what's the degrees of freedom within? It's just the total sample size, our total N, 14 kids, minus 1 for each group. So it's 14 minus 3, right? Because it's you can also think of it as it's the 4 minus 1 plus 5 minus 1 plus 5 minus 1, which is the total number of 14 minus 1 minus 1 minus 1 minus 3. It's just the total N minus how many groups there are, which is 11. Okay, so we put that into the ANOVA table. Great. And then let's calculate the variance within. That is straightforward. We just divide the sum of squares within by the degrees of freedom within. 34 divided by 11 gives us 3.091. That's our variance within, the S squared, 3.091. Great. So we've done the within statistics. Great. All right. Now, let's switch over to the sum of squares between. We come back to here, right? Here we need that grand mean of 4.786, and we also need the group means. Oops, I think I circled that. Yeah, we need that one. And we also need the group means to do our sum of squares between, because now we're doing, it's not the variability of individual kids around their group mean. Now we're doing the variability of the group means around the grand mean. So let's do each of those. So what we do is kind of a way of organizing it is, here's each of our group means, right? The 3, the 4, and the 7. And here's the grand mean. And we just subtract the grand mean from each of those group means. So this is the group mean minus the grand mean, the second group mean minus the grand mean, the third group mean minus the grand mean. Here's the notation, x bar minus x double bar. X. I used x after talking about using y. I slipped in an x. Same thing, but we know that we don't need to. That's funny. Yes, it's same x y. Remember, it's just. Am I in my intro stats mind, or am I in my stats 2 mind? Is kind of which one do I use? That's funny. Let's keep going. Okay, so at the X, but the key is that bar and the double bar is the group mean minus the grand mean. Okay, so we do that and we get the deviations from the grand mean. And then because we're doing sum of squares, we need to square those deviations. So there's our squared deviations of each group mean from the grand mean, right? And this is where people will lose points. This is where people lose points because they forget, they calculate these three numbers and they'll say, oh, my sum of squares between is just this plus this plus this. I'm done. There's my sum of squares between. No, 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 no. You have to remember, these are part of every person's score. So you have to take the 3.189 and use it for every person in the control group. You have to take the 0.617 and it's for every person in the student intervention group, and the 4.903 is for every person for every student in the parent intervention. So it looks like this. This is what you're adding up. And you could literally write it this way, where you can see, visually, I like this because it just is a clue that, yes, you have to remember that each student in the control group has 3.189 that's related to those between group differences. And the 5 kids in the intervention, the parent intervention, have 4.903 related to the sum of squares between, okay? You could also just take the 3.189 and multiply it by 4, the number in the control group, go back here and just say, I'll multiply this by 4 because there's 4 in the control group. I'll multiply this by 5 because there's 5 in that. And I'll multiply this by 5 because there's 5 there. Same way, but I like this, just kind of hammers home why you're doing it. It's because it's part of every kid's score. Okay, let's keep going. So we add that up. You just add that up across all the groups. And here I've summed it, by each individual group. You add that up and you get 40.357. That is our sum of squares between. And at this point, it's all downhill. It's free sailing from here. We've done the messy work. It's still a bunch of little calculations, but we're making good progress. So we come back to our ANOVA table. We enter 40.357 in the sum of squares between slot. We need the degrees of freedom between, right? And the degrees of freedom between is how many groups there are minus 1, because we're looking at the variability between the groups. So it's the number of groups, k minus 1. You have 3 groups minus 1. Our degrees of freedom between is 2. The variance between is the sum of squares between divided by the degrees of freedom between. So that's just 40.357 divided by 2 gives us 20.179. That's our variance between. Okay. Then we're ready to do the F. F is just the variance between divided by the variance. Typo. Dang it. It's the variance between divided by the variance within. Make sure you fix that. That's variance within. Shame on me. Okay. 20.179 divided by 3.091 gives us an F of 6.528. That's our F statistic. So we plug that in for F. Okay, almost done. We can then do the total sum of squares is just the sum of squares between plus the sum of squares within. You just add them up, is 74.357. Degrees of freedom, we do the same thing. Add up our degrees of freedom between, degrees of freedom within. We get the total degrees of freedom is 13. Now all we need to do is calculate our p-value. And, right, we know our F is 6.528. We know the degrees of freedom is 2 degrees of freedom between, 11 degrees of freedom within. Kind of based on this distribution, the F distribution in this case looks a little different than the other example, because like I said, the shape changes based on, based on the degrees of freedom. So this is the shape when you have 2 and 11 degrees of freedom, 2 between, 11 within. Okay, our observed F was 2 with 2 and 11 degrees of freedom was 6.528. It's kind of out here. Our p-value is going to therefore be the area beyond that. What's the probability? I've shaded it and it's kind of small, that little blue. It's the probability that just randomly we would get an F score of 6.528 if the null is true, right? This is all based on an infinite number of samples. If I got a sample, you got a sample, they got a sample, everybody gets a sample, and the null is true, and we all took samples and calculated Fs, this is what the distribution of our Fs would look like. What's the chance I would have just randomly ended up with a 6.528 way out here if the null is true? So to do that, we need to find the area beyond 6.528. I'm going to write that down. 6.528. And it's 2 and 11, because we'll do that using F-score magic. So we are going to go to the last of the magic calculators. And let me pull that over here. Please, I hope I'm sharing the screen and not the window. Can you see that? Oh, good. And let me hide some stuff here. Well, let me hide. Okay, well, there's just kind of the instructions we can see. Okay, so in this case, I know my F score, and the question is, what's the area above it? That'll be my p-value. So I know the F score, and I need to plug in the area here. So we just like the T and the Z. Oh no, it's not the last one. Next week we do the chi-square. So we still got more magic to come. So I type in my F score, and it was 6.528, and the degrees of freedom between was 2, and the degrees of freedom within was 11. And there we go. Here's our values. And notice it's a lot cleaner because the F is one-tailed. The F is always one-tailed because you can't get negative F values. It's always one-tailed. There's no two-tailed Fs. No lower tail. It's always, so it's very simple. And in fact, I've gone so far, call me crazy, I've gone so far as to tell you, hint, this is the p-value. If you're not sure, this is the one you want to report for your F, 0.0135. No doubling, no nothing, there's your p-value right there. We've calculated it. So let's come back to here. There we go. The area above, I've rounded a little bit to 0.014 for this slide, right? So that's the area. That's only 1.4% of the time would we have randomly ended up with an F this big, an F of 6.528 with 2 and 11 degrees of freedom if the null was true. Yeah, we're not that lucky. We're not that lucky to hit this. It's so uncommon. So with a p of 0.014, we're going to reject the null hypothesis. And we put that value, that p-value in our table, okay? So now we've completed the ANOVA table, all right? Now, and we know we're rejecting the null. If we can come back to the F distribution one more time, and before we leave, let's look at the critical F while we're at it. And we can do that. We'll just come back here. But now for the critical F, kind of what's the F score that I need to reject the null? Now we know we already know we rejected the null, but what's the F score I need to reject the null? So in that case, I have to go from the area to F. I know the area is, that'll be my alpha level, right? 5% of the time. What's the F score that gives me 5% of the distribution, more extreme, with 2 and 11 degrees of freedom? So my area is 0.05. Degrees of freedom between is 2. Within is 11. And here we go. And I've even given you another hint. This is the critical F, is 3.982. That's the F score I need to reject the null hypothesis. And again, ours was 6, so it makes sense. We did reject the null. So if we get that piece of information there, we can put it into the figure. 3.98 is our critical F, and the area above that is 0.005. And like we saw, we got an F of 6.528. So yeah, we are definitely in that region of rejection, right? And we know P is going to be less than 0.05, even though we just actually calculated P. That's why, it's nice to actually calculate the P. Here, we just know it's less than 0.05 because it's in that region of rejection. But we know it more precisely than that. So we can come back, let's summarize it. And kind of here's where we left off. And let's keep going. So our results, we had an F with 2 and 11 degrees of freedom, gave us an F of 6.528, which has a P of 0.014. Don't use tables. Don't use tables. This is why we're using anyway. And our conclusion is we will reject the null hypothesis. All right. The kind of, that's the statistical conclusion. Substantive, kind of how would you explain this to your 95-year-old grandfather? Would be something like, well, it looks like there is a difference in the number of hours students engage in this free reading based on whether they're in the control condition or or one of the 2 intervention groups. We don't know where the difference is. Well, actually, this is good because I didn't say this before the break. We don't know which groups are different. Maybe all 3 of them are different. Maybe only 2 of them are different. We don't know. The ANOVA doesn't tell us which ones are different. It just says there's a difference. At least 2 of them are different. You don't know which ones. Now, that may seem, and this is part of the reason why, well, anyway, there's because you don't know which ones are different, it's kind of one of the more I don't want to say frustrating. It's a limitation of an ANOVA all on its own, because inevitably people want to know which ones are different. And there's some strategies you can do about that are in like the next class. Future courses that let you start to do comparisons of, okay, now I'm going to look at specific groups. And is the child intervention group different from the control group? Is the parent intervention group different than the control group? You can start to do those, but there's several ways that you can approach that without just inflating your type 1 error. Because if you think about it, when we did talk about this before the break, if you just did a bunch of t-tests, each of those t-tests has a 5% chance of making a type 1 error. And so all those t-tests, it'll add up, and pretty soon, sooner or later, you're going to make a type type 1 error. You're going to reject the null when it's true. You're going to say there's a difference between these groups when there's not. So there's people, once you've got this significant difference, and we know there's a difference in there somewhere, there's follow-up tests you can do where you adjust your alpha levels to take into consideration. You adjust, there's a few different ways you can do it, but where you make adjustments to the analyses so that you don't end up in, you keep an alpha of 0.05. You don't end up with a bigger alpha because you're doing all these follow-up tests. There's a few ways you can approach that. But kind of for us, in our class, the key is that the ANOVA doesn't tell you which ones are different. It just says there is a difference going on here. Okay. One other thing, just thought I'd point out while we're here. Notice, and we talked before the break about, notice I'm using the S squared for this column. This is where you will often, well, you will often see where someone might write MS for mean square, or literally write mean square in these ANOVA tables. So if you're looking at another source and they have an ANOVA table and you see MS, it's just the mean, it's just the variances. That's just, but you'll often see the notation of MS for the S squared for your variances instead, or they may spell out mean square. But this is one place where you'll often see it in articles and stuff. But same thing. We like, well, I like, and because I like, you like using S squared because it's more clear that it is a variance, and you're not stuck kind of wondering what's this mean squared thing coming out of the blue doing. Okay. So that's our example. We're right at the end. Any questions? If not, make sure you print off the slides. Fix the typo with the between. The numbers is the right number, so it's kind of obvious. You'll see it once if you forget or don't remember that. But the this is one. Just follow the steps. There's a lot of steps. Just follow the steps. Don't be a hero. Don't try to be a hero and do it from memory. Follow the steps, follow my handouts to go through that and think about it as you're doing it. What's the variance? Why does this work? That's good. But otherwise, have a good rest of your week then.
Thank
Take
you.
care.
Thank
Bye,
you.
guys. And I will stop recording at this point.
Thank you,
Thank you.
Professor.
Thanks, guys.